A young scientist is interested in studying the effect of not producing or producing very little protein from gene A. Gene A is linked to a heart condition, causing the heart wall to thin. The scientist's problem is that he is unable to find cells with a mutated gene A. The scientist is looking at two approaches, RNA interference and CRISPR. The goal is to use one of these methods to reduce or eliminate the expression of gene A. RNA interference can happen in two different ways. It can use microRNA or small interfering RNA. The microRNA process starts with transcription of inverted repeat in DNA. This produces a primary microRNA. The primary microRNA is cleaved to produce RNA with a hairpin. Dicer acts as scissors and cuts the hairpin, removing its terminal loop. One strand of the microRNA combines with the protein argonaute, forming an RNA-induced silencing complex. This complex binds with an mRNA, resulting in imperfect base pairing, inhibiting translation. Small interfering RNA process starts off with a double-stranded RNA from an RNA virus or a long hairpin. Dicer acts as scissors, cutting the double-stranded RNA into little pieces, producing small interfering RNAs. The small interfering RNAs combine with a protein, forming an RNA-induced silencing complex. This complex pairs with mRNA, forming a perfect base pairing, leading to mRNA degradation. A different approach would be CRISPR. CRISPR is a natural system used by bacteria to protect themselves from viruses. When viral DNA is detected, the bacteria will produce a matching RNA known as guide RNA. Guide RNA and a protein will form a complex known as Cas9. Guide RNA recognizes the sequence that needs to be edited, in this case the virus, and it leads the Cas9 to the targeted DNA. Cas9, a cutting enzyme, cuts the target DNA. Using CRISPR, scientists can engineer any DNA at the precise location by making a matching guide RNA. The scientist could use CRISPR to make a guide RNA to match the heart gene. He would then add guide RNA and Cas9 to a solution to inject into a patient who has the heart gene of interest. The guide RNA will lead Cas9 to the target DNA, where Cas9 will make the cut. The scientist can make a healthy DNA sequence to insert into the patient where the cut was made. The scientist reflects back on the two methods. RNA interference directs gene silencing, ultimately reducing gene expression. CRISPR cuts and edits DNA, physically altering it. The scientist ultimately chose RNAi, as this method silences the gene, reducing this expression. This is exactly what he wants, so he can research the heart gene. Even though he could edit the DNA using CRISPR, it's risky as cuts are error-prone and can result in unwanted mutation. A mutation could change in the heart's original gene expression, resulting in inaccurate data.